Okay, so we have been looking at several examples of dynamic programming algorithms, and I am aware that I owe you a couple of more that I will create as quickly as I can here. To get even more practice with dynamic programming algorithms and other kind of algorithms, one of the most important sources of problems is the LeetCode website. And you can do LeetCode problems without paying anything, but it turns out if you choose the premium level of account, which does cost something, you can find out which companies are asking which kinds of questions. And this can be very helpful and probably well worth the price of a moderately priced textbook. So I'm going to just show you how to go about setting up an account and accessing LeetCode to learn more about practicing writing algorithms. Okay, so I'm going to create my account by okay. So I've gone to LeetCode.com, and this is my startup screen, the home screen. I'm going to create an account. Okay, and I'm going to use John K. Ostlund as my account name and come up with some kind of a password. I'll come back to you after I've created my password here. Okay, now I need to give them an email address. Let me use my Andrew email address. I guess in that case I'm just also going to use my Andrew ID as my account name. Hopefully that won't conflict with anything. And I'll sign up. You have not verified your account. Okay, so resend the verification email. All right, so it sent me a verification email apparently, which I will look at. Let me sign off for just a moment while I look at my email. Okay, so here is the email that LeetCode sent me. Thanks for signing up. You must follow this link to activate your account. So I'll click on that link. Please wait for a moment. Congratulations. And I want to sign up for premium. So for premium LeetCode, you can get a monthly subscription or you can get a yearly subscription. I'm going to go ahead and blow the $159 on a yearly subscription. Subscription policy, terms of service, blah, blah, blah. I agree. Hopefully they won't come and take my car from me for whatever I'm agreeing to here. Click continue. And now I have to type in payment stuff, so I will do that and get back to you when I'm done. Okay, so I have paid my money and checked out, and now I'm given this survey that I can go through. Frankly, I'm going to just blow this off. And there we are. So now I want to go to Problems. And I can see here that there are 1,553 problems available for me to try to solve. Since I have a brand new account here, I have solved 0 so far. They divide the questions into 3 levels of difficulty: easy, medium, and hard, and I've solved 0 of each of those categories. Okay, and here's also my to-do status. Now, if I'd like to find out on a company basis which companies are asking which kinds of questions, and of course this is not guaranteed to be absolutely right, but it's a reasonable approximation of what's currently going on. I can click on tags over here, and I can click companies, and here I have a list of companies that I might be interested in interviewing with. For example, if I check Goldman Sachs. Now, the list that you get may be in a different order than what I'm seeing here, but for me, Google is at the top, Goldman Sachs is next, and so forth. So for Goldman Sachs, here are questions that are being asked, and I can just click outside that tags list, and I have a frequency of how often these things are being asked, as well as the the difficulty level and what the actual questions are. And so I can scan down through here and see which kinds of questions are being asked. Okay, the median of two sorted arrays is hard and apparently reasonably frequently asked. Trapping rainwater is hard and apparently frequently asked, etc., etc. I can reorganize these in descending frequency order by clicking on the frequency title a couple of times. And so this may or may not give me a good suggestion as far as how I should approach testing myself on programming questions, algorithm questions that are of interest at Goldman Sachs. Again, not guaranteed, but a reasonable starting place. Now let me try another company. Let's see who else I can find down here. Okay, Bloomberg, Morgan Stanley. Okay, so here we have Morgan Stanley. Best time to buy and sell stock. Let's say, who else we've got in here? Airbnb. JP Morgan. Okay, and so you can see for many companies that you might be interested in applying to, which kinds of questions they ask, and that can give you a starting place to decide which ones of these questions to try out. All right, let's do this first easy question just to get used to the LeetCode user interface for doing our programming. I'm going to click on happy number here, and up comes the screen that describes the problem in the left half of the screen and allows me to define code to solve the problem in the right-hand side of the screen. In my user interface window here, Python 3 is the selected language, and so what I'm being shown here is a class solution which has within it a single method called isHappy. Now, if your interface comes up with some other language selected, like C++ or Java or whatever, if you know those languages, you can, of course, go ahead and write the code in that selected language, but I'm going to do my coding in Python 3. Okay, so here's my Python 3 interface. This interface window has pretty small text on it, so I'm going to hit Control+ a few times to make it easier for you to read. So come on, Control+. Hey, come here. Control+. There we go. Okay. That's maybe too big. All right, so there we go. So hopefully you're going to be able to read that. Now, there are a couple of things in this Python code that you may not be familiar with. First of all, I'm specifying here that the second parameter to the isHappy method ought to be an int value, and following that, I'm specifying that the isHappy method should be returning a bool. Now, in fact, those are really just recommendations, which is why I don't I don't usually bother talking about them. They're sort of like documentation. Let me flip to an ordinary idle interface to show you what I'm talking about. So here is an idle interactive shell. Now let me define a function. I'm just going to call it fun1, let's say, that takes an argument which we'll say is supposed to be an int. So n is supposed to be an int, and this thing is also, fun1 is supposed to return a bool value. Following that, I have my colon, because this is the first line of a function definition. And now I indent my body of code, and I'm just going to say return whether n is greater than 10, whatever. So I have now defined fun1, and if I call fun1 by saying fun1 30, okay, the parameter n in the fun1 function definition or function execution gets set to 30, and because 30 is greater than 10, this is going to return true. And if I say fun1 of 0, it returns false. But I can also say fun1 of hello. I get an error message, but I don't get an error message because n is supposed to be an int. I get an error message because this comparison, the greater than comparison, is not defined when I have a stir on the left side and an int on the right side. Okay, so the fact that I have claimed that n is supposed to be an int isn't actually checked, and I've passed in a stir in this case. If I call fun1 by saying 7.89, I'm not going to get any error. 7.89 is not greater than 10. Consequently, I just get a value of false returned. And I don't get any complaint from Python about the fact that this argument value, 7.89, is not int, which is the suggested or documented argument type for n. Let me redefine, well, let me just define a new function, fun2. I'll say define fun2, where n is supposed to be an int, and the function is supposed to return bool. But now let me return n plus 2. All right, well, n plus 2, no matter what kind of thing n is, n plus 2 is n plus 2 is definitely not a bool. If I say fun1 of 5, I get back the integer 7. If I say fun... All right. All right, well, I made another silly mistake here that doesn't matter. I claimed I was going to define function fun2, but then I redefined fun1 by accident. All right, so fun1 receives this integer value 5 and returns an integer value 7. I don't get complained at that 5 plus 2 is not a Boolean. And if I say fun1 of 2.3, that gives me back a float value. If I say fun1 of true, now this may or may not surprise you, depending on how much you remember about conversions. But it turns out that if I take a value true and I add that to an int, the Boolean value true automatically gets converted to the integer value 1 in order to perform that addition. So I get back an integer value of 3. Okay, so the bottom line here that I'm trying to get at is this colon int notation in the parameter list, as well as this arrow bool notation as the return type description. Those are really just documentation, and when you execute the code, they're not really enforced. They're not enforced at all. All right, so here we are now back in our LeetCode interface. And we've got a class solution. We've got the first line of the definition for this isHappy method. And our job here is to complete the definition of isHappy in such a way that this produces the correct answer. All right, so let us now take a look at the problem description. I'm going to slide the code over to the right a bit. Write an algorithm to determine if a number is happy. A happy number is a number defined by the following process. Starting with any positive integer, replace the number by the sum of the squares of its digits, and repeat the process until the number equals 1. Once it's equal to 1, it will stay at 1. Why is that? Because if we replace 1 by the sum of the squares of its digits, well, there's only one digit, which is 1, and the square of 1 is 1, so we replace 1 by 1, and in that case, we'll simply stay at 1. Now, the other alternative is, if we don't arrive at 1, then we're going to find ourselves in some kind of endless cycle that does not include 1. So those are the two possibilities. Either we arrive at 1, or we never arrive at 1, and we end up in some kind of cycle. Those numbers for which this process ends in 1 are happy numbers. So we want to write the code to implement isHappy to detect whether n is or is not a happy number under this definition. We're going to return true in the case where we discover n is a happy number, which means that we end up at 1, or false otherwise. Now, as an example, they show us that 19 is a happy number because 1 squared plus 9 squared is 82, 8 squared plus 2 squared is 68, 6 squared plus 8 squared is 100, and 1 squared plus 0 squared plus 0 squared is 1. So by splitting each value up into its component digits and squaring those digits and adding together, we find that we arrive at 1, and once we've arrived at 1, we've identified this thing as a happy number. Okay, well, let's first try to solve this not by being terribly clever and just walking through the steps. Write an algorithm to determine if a number n is happy. A happy number is a number followed or defined by the following process, starting with any positive integer. All right, so let's just take that as is and make sure that we're starting with a positive integer. Okay? We can actually write that in code. We can say if the type of the argument passed in is not an integer, then we can return false, and we're done. Now, I don't know if I have shown you an example of this kind of comparison before, but it's perfectly fine in Python to ask for the type of some object and compare that directly to an existing data type name. So if n comes in and it's not an integer, then obviously n is not a happy number and will return false. Otherwise, it must be an integer, and so our next test is going to be if n is less than or equal to, well, we'll just say if n is less than 1, then we'll also return false. All right, so now we've confirmed that we do have a positive integer as our argument. What next? Okay. Replace the number by the sum of the squares of its digits. So we're going to be modifying n here, and eventually, if the number equals 1, we will be done. So let's say while n is not equal to 1, we're going to do something with n, and I'm not sure what we're going to do yet. But if we get down here, return true. All right, so while n is not equal to 1, we're going to modify n. If n eventually becomes 1, we'll be done. And at that point, we can return true, because if n equals 1, we have discovered that n is a happy number. Okay, so I've left out all the hard part. So let's do that next. Okay, replace the number by the sum of the squares of its digits. So we need to break this number down into its constituent digits. We can use a combination of modulus to get the final digit in the number and floor division by 10 to get the remaining part of the number without that final digit. So let's, for example, whoops, sorry. I was in the wrong window. So let me just put in a comment here. So for example, 1, 2, 3 mod 10 is 3. 1, 2, 3 floor divide by 10 is 12. So that's the core idea here. We're going to decompose n into its final digit and the digits above the final digit. All right, so fdig is n mod 10, and updigits, that's stupid variable name, but the upper digits are going to be n floor divide by 10. And let's see, the number by the sum of the squares of the digits. Let's see, so we've only gotten one of the final digits at this point. So actually, it seems to me what we need to be doing in here is saying while n is greater than 0, compute the final digit and the upper digits, and let's collect up all these digits into a list. Okay, I'm just making this up as I go. I'm not trying to be in any way clever at all. So I'm going to say digits plus gets fdig. Okay, so now I'm creating a list of these digits. And rather than updigits, let me just use n here. So n gets n mod 10. So I'm going to strip off the final digit, and then I'm going to modify n to be the remaining upper digits. We're going to keep doing that while n is greater than 0. This makes me really uncomfortable. I don't typically want to be using n for two different purposes in two different loops. So let me instead say n2 gets n, and while n2 is greater than 0, then the final digit is the final digit, and 2. And okay, so at this point we must be done. We must have created this list, digits, containing a list of all the individual digits in the number n. Alrighty. Now, what we want to get is the sum of the squares of these guys. And again, I'm going to be very unclever. So sum SQ is going to be equal to 0. And for j in digits sum SQ plus gets j squared. So now we've got the sum of the squares of the digits. If, let's see, repeat the process until the number equals 1. So at this point, if the number equals 1, well, actually, aren't we? We're ready to just say m and gets sum SQ. Okay, because we've computed the sums of the squares of the digits, and that's going to be our new value for n. Replace the number by the sum of the squares of the digits. Okay, so that's what we're doing there. Now, if n is 1, we don't have to do anything further, and we can return true, and we're done, correct? All right, so let's see what we got so far. Very, very unclever, just, just reading the instructions, writing things as they pop into my head. So while we haven't arrived at n equal to 1, while n is not equal to 1, we're going to construct a list of the digits that make up n. Then we're going to compute the sum of the squares of those digits, and n is going to be set to that sum of squares of those digits. If that number is 1, we're finished. Otherwise, okay, now the otherwise is the painful part here. It loops endlessly in a cycle. How are we going to keep track of a cycle? Well, this could be painful if we try to set up something like a circular linked list that we keep adding items to, and then try to test whether the value that we've just computed is somewhere in that cycle. Let me suggest that we can just keep track of these values in a list and not worry about whether it's cyclical or not. If we compute a particular value of n, and we have seen that value of n before, then we must be in a cycle, right? Because if we compute the sum of the squares of the digits of a certain value of n, and we get that, and that leads us to getting that same value of n again, then we must be in a cycle somewhere. All right, so let's not worry about trying to create some kind of circular structure. Instead, maybe what we should do is just keep a list of digits seen, and the list is initially empty because we haven't seen any, or no, it's not digits seen. Digits are the individual digits. N vowels. So we want to keep track of the n vowels that we've seen. And initially that list is empty. Okay. Else, okay, we want to find out now, is this value of n that we've just computed, is that a number that we've seen before? And we'll say if n is in the n vowels that we've seen, then we must be in a cycle. We've seen that number before. We must be in a cycle, and so we'll just return false. On the other hand, if n is not in the list of values that we've seen, we should append it to the list of values that we've seen. So we'll say n vowels seen, and I'm prone to be using operators, so I would tend to write it like this. You know, we've seen this value of n before, but you could just as well say, of course, n seen dot append n, doesn't matter. And actually, I just realized that we've also seen the very first argument that we were passed in, right? So let's have that be a value that we've seen already. If we come in with some value n, and we do our algorithm on n, and we get the same value back, well, now we're in a cycle that's just stuck on itself. 1 is probably the only value, well, 1 is, I think, definitely the only value that could happen with, but anyway, we'll just say, all right, we've seen n. Okay, so the number is happy if it is an integer and it's positive and as we go through this while loop, as long as n is not equal to 1, we compute the sum of the squares of the digits. That becomes our new value for n. If that value for n is 1, we're done. Otherwise, if we've seen the value before, whoops, we better return false. Forgot to say return. Otherwise, we're going to append that value to our list. Okay, now, again, I'm not being very clever. I'm just kind of writing this as I go. And I just noticed one thing that we can obviously do better here. I'm saying if n equals 1, return true. Now, that's actually our loop condition up here. So let me get rid of all that. Let me get rid of those two statements. And we'll just say, at this point, we'll say if n is not equal to 1, and n in n-vals seen, then return false. Else. Okay, so we're going to compute the sum of the squares of the digits. If the value that we get isn't 1, and we have seen the value before, then we're going to return false. Otherwise, we'll add n values. We'll add n to the list of values that we've seen. All right. Well, I haven't even tried to compile this thing yet. Let's see what we get. Let's run the code. Your input 19, output true, expected true. Yay! So that worked. Let's try now to submit the code. We've had one test case and it's worked. Let's submit the code and see whether it works according to their. Okay, run 52 milliseconds, faster than 25% of the online submissions. Only faster than 25%. That's not very good. We were successful. That is good. Memory usage was 13.8 megabytes, which is less than 2/3 of the online submissions. So that is good. We're slower, but we didn't take as much space. Cool. All right. So far so good. Now, if you did make mistakes in your code, if you made mistakes in your logic, you would get error messages, you would get complaints. I probably should demonstrate that. So let's let's just intentionally wreck something. If I don't include my colon there and I run the code, I get an error message, as we would expect. If I do something silly like saying while n is not equal to 0 and I run the code, well, this is probably going to just run forever. Judging. Yeah, I've created an infinite loop. Time limit exceeded. There we go. Okay, cool. Whoops. So I have correct code, but you can see that you will get errors. you will get time limit exceeded, those kinds of things. Now, actually, there's something we can do that will make this quite a bit more clever. We don't really need to keep track of a list of values that we've seen before, because when we search the list, when we ask later on whether n is a value that we've seen before, we don't really care about the ordering in which we see these values. And the list is going to keep track of these things in the order that we saw them. But searching a list is an order n operation. As the list gets longer and longer, it's going to take longer and longer to search. We don't care about the order. We only want to know, have we seen the thing or have we not? So rather than using a list, we can speed things up by using a set. And we can create the set by just using curly braces and putting n as the first value in our set. We'll then have to modify this append down here. Append is a list operation. We'll need to change that to add, which is a set operation. So that should work fine, and it should speed things up. So let's run the code. All right, so that one test case was valid. Let's submit the code. And cool. Runtime is 48 milliseconds, faster than 30% of the solutions. Memory usage is less than 44% of the solutions. Okay, a little better. Now, what else can we do? Well, it's not necessary here to keep track of a list of the individual digits when we compute the sum of the squares of the digits. We can really just process these digits as we go. So instead of creating this list of digits first and then figuring out the sum, let's just do this all in one step. Let's get rid of this. And we can just say sum of squares is 0. And n2 is n, just because I don't like to directly modify n while I'm messing around with pieces of it. And I'll just say while n2 is greater than or equal to 0, let's just set the sum of squares to n2 mod 10 squared. And then we modify n2 to be itself over 10, and like so. And then I don't need this stuff. Okay, so we're going to set our sum of square variables to 0. We're going to set n2 to n, and then while n2 is greater than 0, we'll add the square of the lowest digit into the sum of squares, and then reduce n2 by a factor of 10 using floor division. And all right, that looks better. Should be a little faster. Whoops. All right, I press Control S, and it's asking me if I want to save my stuff into an HTML file. I don't want to do that. I did it by accident. So let me just run this code. Yay, that was accepted. Let me submit the code. Okay, so 36 milliseconds, faster than 2/3 of the submissions. Memory usage 13.6 megabytes, less than 95% of the submissions. Not bad. Okay, I don't think we need to poke around with that any further. So there's what we do. We are presented with class solution, and we're presented with the interface to the method within that class that we need to define. The method is called isHappy. It takes self as its first argument, like any method of a class does. And then it takes an integer as its second parameter, and it returns a bool. And we have an algorithm that works. Cool. All right. So that's an example of an easy, what they call an easy test. Let's return to our problems. Get back to problems. There we go. All right, so I want to get back to problems. I want to get back to the JP Morgan problems. Let me pick tags, companies, go down to JP Morgan. There we go. And look at that. I have solved one easy problem. Cool. Okay, so that was one. Now let's now solve a medium problem, which is the coin change problem that we did. This one will require the use of the dynamic programming algorithm that we talked about. You are given coins of different denominations and a total amount of money. Write a function to compute the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any combination of coins, return -1. Okay, so that's exactly one of the situations that we covered in one of the lectures. So let's give ourselves some room to write some code. Once again, we have class solution, and the method in here is called coin change. It's going to take a list of coin denominations called coins as its first parameter. Well, you know, after self, of course. And then it's going to take an integer amount as a second parameter. When we're done, we're going to return an integer, which is either going to be 0 or more if we are able to make change, or -1 if we cannot make change. All right, so let's go ahead and code this up. Okay, so what we need is a two-dimensional array. We could use a NumPy ND array, or rather than fuss around using import and so forth, let's just go ahead and use a list of lists. We need the rows to represent the individual coins, one coin at a time as we add those coins to be considered, and the columns will be for value amounts from 0 up to whatever amount was passed in as an argument. Well, a list of lists sounds awfully like we can use a comprehension for this. So let me first do our type checking. We'll say if type of coins is not equal to list, or type of coins sub 0. I'm probably being overly paranoid here, but I don't mind paranoid. So if the type of coins is not list, or the length of coins is 0, or the type of coins sub 0 is not int, then we'll just return -1. Okay, so if the coins parameter is not a list, or if there are no coins in the list, or if, well, I guess technically I should test each one of the coins. I'm sure I'm being overly paranoid here, but whatever. I've done some reasonable testing here. And I'm also going to test if the amount is less, well, if the type of the amount is not equal to int, or amount is less than 0, return -1. Finally, if the amount is 0, then I can just return 0. Whoop, forgot my colon. All right, so now we're ready to actually do something interesting. We have a list of coins. We have an amount that is greater than 0. What we need to do is to create this list of lists. So this is going to be coin versus amount. Coins are the rows, amounts are the columns, and we'll use a comprehension to set this up. So for each row, 0 for j in range amount +1. Okay, and remember I'm using the amount +1 because I need to go from 0 up to and including the amount. And I'm going to do this for C in coins. All right, now I would like to just make sure that my dimensions here are correct. So I'm going to just print coins versus amount and return a -1. Okay, now this is not an answer, but it is code that I do expect will compile and will run. So I just want to run this code to test whether I'm good up to this point. I hit run code. There we go. So I've got 3 coins. My value is 11. And I've got 3 rows of 12 zeros. Cool. All right. So let's get back to work. Let me get rid of my print. I'll just comment it out actually so I can leave it in there for now. Now, we need to fill in our table based on the formula that we came up with. So, we've got 3 cases. Okay, big oops. It wasn't terribly long after this point that I discovered I had a significant oversight in my formula described in my original presentation of the coin change problem, that I was missing a comparison between a cell on the current row versus a cell in the row above. So I'm going to clip out a big chunk of this erroneous stuff, but I am going to leave in the error message that I got, as well as my confusion, so that you can see what happens when you do make a mistake. And then we will pick up again using a one-dimensional array with an algorithm that I hope is more clear and that is actually correct. So correctness is a good thing. Okay, so my big mistake is is coming up, and you'll be able to see what goes wrong. Yay! All right, so 2, 3, 6 are our coins. These are taken directly from our course notes, and the amount is 10. The output that we got was 3 coins. Okay, so for 10 cents, we've got 1 6-cent coin and 2 2-cent coins. And the expected result in my test case that I wrote was 3. Now let's cross our fingers and submit. And wrong answer. Output 26, expected 20. Okay, so this is what happens if you are confident that you're right and you're not right. So I analyzed the situation and figured out what I did wrong, and also realized that the algorithm just using a one-dimensional array was actually much easier to write as opposed to trying to patch up my two-dimensional array code. So we are going to abandon this two-dimensional code and implement the one-dimensional array strategy that I have since implemented. And I'll be re-recording and posting that revised algorithm as week 2, part 2, as soon as I get done with this. Okie doke, onward ho. So let us erase all of this bogus code that I wrote. And I no longer need a two-dimensional array, so I'm just going to get rid of all of this stuff. And what we're going to do is to create a one-dimensional array instead. I'm just going to call this thing A, which is the matrix name or the array name that I've used in the revised course notes. And the comprehension here is going to be quite simple. We're just going to use amount plus 1 as our value for j in amount plus 1. What does that mean? Okay, well, so let's suppose that the amount that gets passed in is 10. That's the example in the course notes. Then I want an array of 11 cells for values ranging from 0 up to and including 10. Okay, so I want 11 cells in my array if my amount passed in is 10. And I want a value that's too high as the initial value in each one of those cells. Okay, so I can't need, if my amount coming in is 10, which is, as I said, the example that we're using in the notes, if the amount coming in is 10, then I can't need 11 coins. And so I'm going to just fill in 11 in all of those slots initially, which are impossible values, and let me print the resulting A, and I'll return a -1. Here again, this is not a solution, but I do want to see that my array A has been created correctly. And, okay, int object is not iterable. Int object is not iterable. Oh, of course. I have to say range amount plus 1. All right. There we go. There we go. So now I have an array of 11 11s. And now I can perform my correct one-dimensional algorithm, which looks like so. For each coin, we're going to store 1 into A sub CI, where CI is the current coin. Then, for each value in to, and including amount, what we're going to do is to store the minimum of the current value of, for each value in to amount. So let me replace this with j. So for each j in to amount, we're going to replace, instead of using English, let me just say, modify a sub j to equal the minimum of a sub j minus ci, 1 plus that, or the value that's already in a sub j. Okay, so in other words, for each j going from, ci plus 1. Okay, so we're, let me revise this as well. So I'm going to say a sub ci gets 1. And then for each j going from the next slot up to the final slot, in that slot we're going to store the minimum of what's either already there or 1 plus the value ci steps earlier. Okay, so in other words, I've got my current value j that I'm interested in, and if I subtract the value of the current coin, that gets me back to an earlier slot in the array. So 1 coin plus however many coins I needed to get to that value is one possible number of coins that I need. The other possible number of coins that I need is the number that I've already discovered, and I'm going to store the minimum of those two things. All right, so now let's just write this as code. So for ci in coins, store into a sub ci a value of 1. All right, so ci is a coin, therefore the number of coins we need to represent the value ci is obviously 1. Then for j in the range from ci plus 1 up to amount plus 1, up to but not including amount plus 1, set a sub j equal to the minimum of the existing a sub j, or 1 plus the number of coins that we need to represent j minus the value of the current coin. All right, so now let me just display a at this point and return -1. Okay, so again, I'm virtually done, but I just want to see the resulting array. Actually, let me indent this so that I will see the array A after each step. A for coin CI. And then I will print final A and let's run that. There we go. Okay, cool. So the initial A was just all 11s. Then, if I only consider a coin with a value of 2, I cannot produce a value of 0. I cannot produce a value of 1. I only need one coin to produce a value of 2. I can't produce a value of 3. I need 2 coins to produce a value of 4. 3 for 6, 4 for 8, 5 for a value of 10. Now, if I next consider coin number 3, well, I only need one coin to represent a value of 3. I need 2 coins to represent a value of 4. All right, the coin number 3 won't help me because the minimum of 3 plus 11 versus 2 is going to be just 2. I need 2 coins to represent a value of 5, 2 coins for 6, all right, 2 3-cent coins for 6, 3 coins for 7, 2 4s and a 3, only 3 coins for 8, because now I need 2 3s and a 2 as opposed to 4 2s, and so on. And when I get down to the final version of A, what I discover in the last slot is that I only need 3 coins out of this collection, 2, 3, and 6, to represent 10 cents. And for this small a number of coins, the answer is really obvious. I need a 6-cent coin and 2 4-cent coins to represent 10 coins. So that looks like I really got it this time with much less code. Let me comment out this print. And now, what are we going to return? Well, what I want to return is A sub minus 1, the last cell in A. But if that happens to be 11, if A sub minus 1 is greater than the amount, I actually want to return a minus 1. Otherwise, I want to return A sub minus 1. There we go. And I'm not sure whether I did or did not mention this in the Python Basics course. You can also use what's called an inline if-else. So you can say to return A sub minus 1 if A sub minus 1 is less than or equal to the amount, otherwise minus 1. So that's a more compact way of describing the same logic. I'm just going to leave my original logic in and just comment this out. Let's run the code. All right. All right, I'm still printing something. I don't want to print anything anymore. Why am I printing? Oh, I'm printing this stuff. All right, so I'm going to get rid of this print. I'll run the code. Okay, so for this small example, 2, 3, 6, with a value, coins 2, 3, and 6 with a value of 10, the output that I got was 3, and the output that is expected is 3. Now let me bravely submit this again, and this time, what? Okay, if I just have a coin of 2 and a value of 1, that should be returning a minus 1. Why is that not returning a minus 1? Let me pose that as a test case. So I have a coin of 2 and a value of 1. I'll run the code. List assignment index out of range. Oh, well, duh. Okay. I need to add an if in here that I forgot. So I can't consider a coin that is too large to even fit in the array. So if Ci is greater than the amount is less than or equal to the amount, then I can do all of this logic. There we go. Otherwise I can't. Oops. All right. There we go. All right. So that time I got it to work. Faster than about half, memory usage less than 60% of the submissions. So we could tweak this to speed it up, and we could tweak it to occupy a little less memory, but we got it. All right, well, that was a bit of a struggle, but anyway, the purpose of this was to show you how to use LeetCode. And I manually typed in my code interactively here. You, of course, can write your code in advance and then copy and paste it into LeetCode rather than manually typing things in. Now, of course, when you are faced with a test from a potential employer, you will end up having to manually type stuff in. So you won't be able to copy and paste in that case. But if you're practicing writing algorithms and you want to just confirm that the algorithm that you wrote is correct, then of course you can copy and paste from idle or spider or PyCharm into this LeetCode editing window and test to see whether your code is correct. Now, you will, if you're being, if you're doing an interview test, you will be timed. And so I recommend that you not do this paranoid stuff that I did of checking the types and the lengths of all of the parameters. You can be assured that if the problem specification says that the arguments will be of a certain nature, you can assume that they really are of that nature. I've been writing code in commercial environments for a long time, and in that kind of environment, you have to assume that your user is going to do every possible idiotic thing under the sun, and you need to protect yourself from what users might do. Now, one way of handling that situation of having a user making mistakes is to just have your code crash and blame the user. And you say to the user, well, user, you're stupid, you didn't use it the way you were supposed to, it crashed, that's your fault. For library code, where efficiency is an important matter, that might actually be an acceptable approach, but most of the time, in most circumstances in commercial software, it is not an acceptable solution to just have your program crash and then when the user calls up to complain to say, well, you did something wrong, it's your fault. Nobody is going to be impressed if you write code that just crashes anytime a user does something wrong. So there's my editorial comment. And okay, so that is good as far as talking about LeetCode. Oh, there is a solution given that you're welcome to look at, of course. For each one of these problems, there is a solution given. And there's a description, an outline of the algorithm, and then there's some code. Now, the code may not be in Python. It may be in some other language. Here it's in Java. And then they will describe various accepted solutions. Here they accept both a top-down approach to the problem, which is recursive, but you should use memoization of this tree. And they also accept a bottom-up solution, which is the one that I implemented. And here we have some Python code for that implementation. This is basically what I did, but in a little less, a little fewer number of statements. Okay. Now back to, I'm going to get back to my problems, and I just want to point out that in your search for problems, you can actually search for dynamic programming. And you'll get all kinds of dynamic programming problems. And if you double click on frequency, you'll get them ranked by how often they're asked. This is not just by financial companies, it's by any old companies. And in fact, if you can select dynamic programming as a topic. There we go. And so apparently there are 215 dynamic programming related problems. I have done the coin change problem, and I also did way down in the easy stuff. Interesting. I'm not seeing it. In any case, it is trendy right now for companies to ask dynamic programming problems. And so you should do not only the ones that I've described sort of as a starting point, but you should make it a point to do as many of these things as you can. You can start by looking at all the various financial companies and ranking their dynamic programming questions by frequency. Do the easy ones first to make sure that you're comfortable with LeetCode and comfortable with the easier algorithms, and then try to move your way up into the medium ones and the hard ones. I will tell you frankly that in the MSCF program we like not to just teach to the interview. We're trying to teach you things that you actually need to know. And there is a strong overlap between what you actually need to know in order to be able to do your job and what you'll be asked in interviews. Dynamic programming is the one case where this may not be quite true. You will, if you're doing programming in the financial world, you will be faced with vast mountains of data that you will need to be able to produce algorithms in order to handle. And so the technique of using dynamic programming for solving those kinds of problems is something that you should be familiar with. But as far as these specific problems, these specific problems of putting items into a knapsack or figuring out how many coins you need to create the minimum number of coins to make change, you're going to see these in interviews. You're going to see these kinds of things in interviews, but it's not crystal clear that you're going to be using that knowledge on a daily basis. So let's be blunt. This is a filtering mechanism. This is a filtering mechanism to try to filter out the people who have done a lot of studying of a lot of dynamic programming algorithms and who have written a lot of code. They're trying to identify the best programmers with the most experience in writing relatively sophisticated algorithms. But that may or may not translate one-to-one in what you actually need to know in order to be able to do your job once you show up at your internship. Okay, well there's another editorial. All right, so that's LeetCode. There is another thing that you might be interested in called AlgoExpert at AlgoExpert.io. This is another tool that claims to prepare you for interviews with tech companies similar to LeetCode. if you exhaust LeetCode and you want more practice, you might be interested in having a look at AlgoExpert. And of course, there's also things like Geeks for Geeks.org, which has a whole bunch of categories, both about the Python language and various other programming languages. Okay, it wants me to sign in. Don't want to tell them about myself. You can also get categories, okay, algorithms, dynamic programming algorithms, and this is also another source of information about algorithms. And on it goes. Okay, so best of luck. Email me with questions if you have them. I may not be able to immediately answer your question, but with any luck, I'll be able to point you at a useful source of information. Okay, take care.